So we've looked at parametric curves just kind of as functions. Now we want to see how does calculus apply to these and what can we do. Remember, we're going to have, with a parametric curve, we're going to have x and y as functions of t. So they're going to, as we change t, then that's going to sweep out a curve, right? Our location will change with time, and so this curve will be traced or swept out. And the question is, how are we going to find, say, the first derivative of that curve? Or how will we find the derivative of the first derivative? How will we find the second derivative, which measures something about the concavity of the curve? Or how can we, given a starting time and an ending time, how can we find the length of that curve? Or if we take that curve and revolve it around the axis, say, suppose we take this curve and we spin it around the x-axis, then that's going to give us some kind of vase, right? And so this surface of revolution, can we find its surface area? So what's the length of the curve, or what's the area of the surface of revolution? Those are the four things that we want to talk about as far as calculus on parametric curves. So let's think first about the slope of a parametric curve. See, normally if we had y as a function of x, then we would just find the slope by calculating dy dx, right? We just take the derivative of this. So the slope would be dy dx. We would just find out for this given function, how does the output change as the input changes, right? What's the derivative of this particular function? But in the case of a parametric curve, we have x, it's a function of t, and we have y as a function of t. So we don't necessarily have a Cartesian equation like this in order to find the slope. So what we can do, though, is we can think about differentials. So we're on this curve, and we might ask, as time changes, so we have time moving forward here, if we make a small change in time, how much will we go over, and about how much will we go up? So from differentials, if we want to figure out how much x changes, we should take the derivative of the parametric equation for x with respect to time and multiply by how much time elapses. If we want to know how much y changes, then we should take the derivative of the y function with respect to t and then multiply by t. If we want to find the slope, then what we're going to do is we're going to take the rise over the run, right? So this is going to be how much we go up when we make a certain change in time, and if we make that same change in time, how much will we go over? So we have our rise and our run, so our slope, that's going to be dy dx. That's going to be the rise over the run. And to get the rise, we're going to take dy dt, right, times delta t. And then to get the run, we're going to get take dx dt, that's the x prime, right, times the change in t. And we come up with this formula, dy dt over dx dt. Or, to write it in Newton notation, we have x prime and y prime, right? So y prime of t over x prime of t. Okay, so that has our slope, which normally we would have to convert this, convert our parametrization into some parametric equation to find the derivative. This allows us to find the slope of the curve just starting straight from the parametrization. We'll look at an example in a second. So there's the key formula. If you understand what's going on with differentials and you understand where the formula is coming from, it's just basically a rise over run. So we'll look at an example in a second, but I want to look at something else. Once you calculate dy dx, then you have the slope as a function of time. So you already have, if you have a parameterization, you can find dy dx. It's going to be dy dt divided by dx dt. So that's the slope. So now you actually have a parameterization of the slope as a function of time. So think about this as a new function that describes the y-coordinate here is the slope for a particular time. Then if you want to find out how that slope, so if you were to graph dy dx, that's going to be a function of t, right? So think about that as your maybe your new y-coordinate. So I'll maybe call it y tilde. And then you still have the same x-coordinate. If you were to graph this parametric curve, this would be a graph of the slope at any point. So if you want to find the second derivative, you need to find the graph of the slope of the slope. But we know how to find the slope of a parametric curve. You just take the derivative with respect to t of the y value, and you divide by the derivative with respect to t of the x value. And that will find the rate of change at which the slope is changing. That's going to calculate d squared y dx squared. That's the second derivative. Remember, the second derivative measures the concavity. If the second derivative is positive, the graph is concave up. It's shaped like a bowl up. If the second derivative is negative, then the graph is concave down. So that's what that measures. Let's see if we could apply this to a particular example. Say it says find an equation for the line tangent to the curve x equals secant squared t minus 1, y equals tan t. That's a parameterization, isn't it? Because our location is given as a function of this parameter t at the point where t equals minus pi fourths. Also find the value of d squared y dx squared, the second derivative of y with respect to x at this particular point. So what we're going to need to do to find the equation of the tangent line is we're going to have to find the slope, right? And as long as we're at it, we might as well find the second derivative. Then we can put it all together to answer the problem. Okay, so we know that dy dx, the slope of the function, is going to be y prime of t over x prime of t. That's just rise over run. Now y prime, the derivative of the tangent, is the secant squared. And the derivative of the secant squared, let's see, that's going to be 2 secant t times the derivative of the secant is the secant tangent. So we get secant t tan t. Okay, so the derivative of y with respect to t is secant squared. The derivative of secant squared minus 1 is 2 secant t sec t tan t. Okay, if you look at this, we've got secant squared upstairs and secant times secant downstairs, so they cancel. We get 1 over 2 times the tangent of t. Or if you like, that's 1/2 the cotangent of t. Now notice that we have the slope as a function of t. We also have our location along the x-axis as a function of t from this equation. So the formula for d squared y dx squared, the second derivative of y with respect to x, is just to find the slope of this parameterization. So we find the derivative with respect to t of 1/2 cotan t, and we divide by the derivative with respect to t of x prime. It's just the same formula applied. Instead of to this y and x, apply it to this y, which gives the slope as a function of x. So apply it to this y and that x. So the derivative with respect to t of secant squared t minus 1. Okay, well, we know the derivative of the cotangent. The derivative of the cotangent is the negative cosecant squared. So if we have 1/2 cotangent, we get negative 1/2 cosecant squared t. Also, if we, let's see, we already have taken the derivative of the secant squared minus 1 once before. We know that that turned out to be 2 times the secant of t times the secant of t tangent of t. Okay, and let's simplify a little bit. What do we have here? We have a negative 1/2 and a 2 down here, so we have negative with a 4 down below. Now what I'm going to do is the cosecant is 1 over the sine, right? So down, if we have cosecant squared upstairs, down below we really have sine squared. Okay, and the secant is 1 over the cosine. So if we have secant squared downstairs, we actually have cosine squared upstairs. And finally, the tangent, that's a sine over the cosine. So if it's downstairs, there's one sine downstairs, and there's a cosine upstairs. So we've simplified this now, and we can see, oh, cosine over sine is cotangent, so now we have negative 1/4 of the cotangent cubed of t. There's our second derivative. So we found the second derivative. The last thing we need to do is to find the equation of the line tangent to the curve. Oh, I guess our second derivative at this point. D squared y dx squared when t equals minus pi fourths would be negative 1/4 the cotangent cubed of minus pi fourths. the cotangent of minus pi fourths is negative 1. So we get negative 1 cubed, that's negative 1 again, times negative 1/4 gives us 1/4 for the second derivative. So we know at this point that the graph is concave up, so it's bowl shaped up. Now let's find the equation for the line tangent to the curve. Well, the slope, dy dx, at this particular time, at t equals minus pi fourths, is, let's see, 1/2 the cotangent of minus pi fourths. And the cotangent of minus pi fourths is minus 1, so we get minus 1/2. So at the same time, the value of y at t equals minus pi fourths is, let's see, the tangent of minus pi fourths is the same as the cotangent, it's negative 1. And x is the secant, right? So secant squared minus 1 would be, when t is equal to minus pi fourths. Let's see, the secant is 1 over the cosine. The cosine of pi fourths is root 2 over 2. So the cosine squared would be 2 over 4, that's 1/2. So the secant squared would be 2. 2 minus 1 is 1. Okay, so now we have 1 for that answer. So to find the equation of the line tangent, we take y minus the y coordinate we know. And we know at minus pi fourths the y coordinate is negative 1, equals the slope. We figured out that the slope was negative 1/2 times x minus the x coordinate at that given time. So we have y plus 1 equals negative 1/2 x plus 1/2. So y equals negative 1/2 x minus 1/2.